I got some criticism on my video, and I realized that it was quite without explanation. And that's partly because it's really for professionals who are making cells. And I'll explain it now. It starts with a thought experiment. And very simple. I fill a jar with electrolyte. And I have a couple of pieces of copper in it. So obviously the voltage is going to be 0. Duh. Now, I interpose an electret into the, sandwich it right between the electrodes. Well, there is no electric field inside a conductor. So we know what happens. This surplus of charge on one side of the electrode is going to transfer right through to the surface, which is the interface between the juice and the plates. Is nothing going to happen? Do you really think it would have no effect on the chemical reaction? And this is what I set out to find out. I thought it probably would, and you know, I can't rule it out. I tried to rule it out, I cannot. But it makes sense that at least this would be a concentration cell, because after all, the charges are going to end up on the outside of the electrodes. There's no way around that. And, okay, the electrodes themselves are neutral. The particles inside there are unaffected until they leave or want to arrive back. If they're leaving, well, they're going to leave with a push. And if they're attracted, great. I would think you're going to have a higher concentration of positive ions on the plate that has the electrons pushed to the outside. There's the principle. Right, I have an important announcement, and I swear it's true. I swear on the good book. The book that is really the story of everything. And the most wonderful thing about this book, so my professors said, if you find something that's not true, they'll rewrite it. The new editions will have your work. I set out to investigate whether there is any role for electrets in electrochemistry, in electrochemical cells. And, you know, I couldn't find any electrets. I had to make one. And after I got it out of the oven, I just had to check and see if I'm barking up the right tree or not. So I mixed up some Drano and I put a couple of pieces of zinc in it. And, you know, I went to measure the voltage. I felt like the stupidest thing in the world, measuring the voltage on 2 pieces of zinc in some sodium hydroxide. Of course it was 0, duh. Well, I stuck my electret in with it. The voltage jumped. Now, I was, you know, I needed 5 hands to do this. I was getting, you know, juice all over the place. I just had to find out. So I ran and called my roommate over to look at it. Well, he doesn't know anything about chemistry and he didn't care about it. He changed the subject, he didn't give a damn. So some people care a lot about electrochemistry and some people don't. But anyway, I'm going to show you what I have. Now, I can't show you the first and second experiment because the first one, you know, things were getting all over the place, and I immediately rinsed my hands off. It was getting on my hands. And I rinsed everything down the drain, and I rinsed off the electret with hot water. Now, I had to leave for a couple hours. I got back, I just had to repeat the experiment. Well, I damaged my electret. You can't do that to them. So I made more electrets, and they are curing right now. And they may take another 3 months to cure. There's your 0. Okay, now, the first thing I didn't have any more electrets, and I wasn't going to have any more electrets for a few months. So I did what the microphone people always do. I'm one of those microphone people. And if you can't get an electret, you do externally energized. And I made this thing. These are zinc on the outside. I could have used iron, steel, anything would have worked, copper. This is another piece of zinc. I use zinc because I thought it's very reactive, and I want to get some kind of results. And this is 3 pieces of glass, so I have a steel plate sandwiching the center piece of glass. And now, unfortunately, that doesn't make a very good electret substitute because this glass is so thick. The electric field diminishes at the rate of about 10 to the minus 11th per meter. Permittivity is very low, and even in something like glass, where permittivity is much higher than free space, okay, what is 12, 15, 20 times as high? That's still nothing. It produced results, and I will show you those results. Now, then after I turned it off, well, it still worked because the glass had the residual electric field, but I wanted to do a little better than that. It was obviously very bad. So I took I used string envelopes. These are, maybe you've seen them before. Guitar string envelopes. Okay, so I have my 2 electrodes. Look what happened. I got an output, and I will show you the actual experiment, but I want to show you what happened. You can see the electrodes look a little different. Now, I'm sure that both of them experienced plating onto and off of, but one of them experienced it more. My guess is it was this one that was onto. I kind of feel it a little raised, this one not. So I'm going to say it was plating onto this one. I didn't keep track. I just didn't even keep track. I'm going to use electrets next time. Now, when I turned it off, and I'll show you this, of course, it continued to operate because of the residual electric field in this very poor, well, I don't know how poor it is. It's a piece of plastic. But, it was at room temperature and it was exposed to about 10,000 volts. But it just stayed like that for weeks. Now, I think it's fair to say that a real good quality electret is going to be between 100 and 1,000 times stronger than this. I'm taking bets. Can I shift the frequency of this solar cell by putting it in electric field? Any bets? All right, 1 camera battery later, we are hooked up to the high voltage. Well, this is not the highest, but it's... Now, as soon as I turn it on, of course, that doesn't count. Change goes through it. But you can see it's pumping all kinds of current. Now, some of that could be leakage current. It's going up and down because the voltage isn't holding steady, which is normal for that supply. And I'm turning it up. It's trying to tell me a mill is going through there. I don't think this thing puts out a mill. See, I'm worried about the leakage current going right through. Well, now it's saying 50. This meter is fluky. Now, if I wanted a meter that wasn't fluky, I could buy a fluke meter. But I don't want to buy a meter that's called fluke. I have to doubt every measurement. Actually, I like the ones with the needles, not the digital. Don't think that could be leakage current. It's just too high. We're looking at it. Now I'll turn the high voltage back off. Now it's stabilized and you can see it dropping. But is that leakage current I'm measuring? How can it be 2 mils of leakage current? I don't think I could do that. I think this thing only puts out microamps. If it put out mils, it would shock me too horribly. But also, I have this little ammeter here. I can tell how much current is flowing. It's very little. And I will show you. Well, I better, well, here. Anyway, there you go. Right between those two screws, see a little spark? That's the current. And it ain't much. I can estimate it by looking at it. I've seen it do many things. But that is the only way I have to measure this, because I can't measure it directly. I'm going to buy 100 10 meg resistors and make a tree. I'll just string them together with a piece of styrofoam, and then I will be able to directly measure up to 200,000 volts. But right now, what I'm looking at is this thing's pumping current. That is not voltage, that's current. So far so good. Next step, of course, is to get rid of the power supply, which could be leaking current. And leaking that much current? How can it do 15 or I can't tell what that meter says, but it's in milliamps. That power supply can't do that. I'm going to turn off the power supply again. At least it makes it more stable when I do that. It doesn't go spark-wise. Alright, my battery's running out on the camera. Goodbye. I am cursed with having the most unbelievable videos. But you know, these experiments are repeatable and verifiable, and I hope somebody out there does it. Now, I filed a provisional patent. Boy, I rarely do that, because you can't make money off a patent. I learned that. I filed a provisional patent on this so that other people won't patent it and keep it from being researched. This thing needs development. Now, there might be other roles for electrets in electrochemical cells. For example, directing ions where you want them, or perhaps suppressing dendrite growth. You can kind of see what I've done here. I've taken something, an electret, in this case simply an electrode that's insulated in a plastic bag. Same thing. And so I've taken a static electric field. It can produce no current. It's insulated. And I have paired it with these electrodes. Oh, they can produce all the current in the world, but no voltage. There is no potential difference, and there was no separator. So there was 0 volts between here before the electret. So I did the same thing as in my last experiment, except in that one I used gravity instead of charge to drive a system that relied on hot air rising and heat going down through an insulated piece of copper. So in both cases I'm doing the same thing. I'm kind of using opposites. That is, there seems to be some kind of parallel there. Now, I beg you to watch my other video. It's about the second law of thermodynamics. And just like this, it can be easily reproduced. Now, if it's true that the second law of thermodynamics could be defeated and that entropy does not go just one way, wouldn't you want to know that? Wouldn't you want to find out? And this is a repeatable experiment, and it's inexpensive, and you don't even have to build the whole thing. So please watch my other video about that. I would think somebody get curious and do it. But I know they're going to get curious and do this, and I hope you do. And if you have a supply of electrets, commercially produced electrets, or you're making your own, please tell me. I need help. Okay, my camera was out of juice, but that's not all it was out of juice. This could be introducing a hum into the recording because it's on charge. I don't care, because now it's getting very important, because now I turned off my power supply, but I realized that the electrolyte was barely touching the zinc on one side, and I filled it up. I put water. So, yeah, I'm a bad experimenter, but that's the way it is. You keep fixing all day, every day. So, it's pumping current. Now, the power supply is off. Let me make sure it stays off. The power supply is off, but now let me short these plates. They're dead. How you could. There. Okay. What's happening here? See, we never know what we're looking at, but I know I'm looking at current. Now, just like with the glass one, there is residual electrical field stored in the plastic from that guitar string bag. Glass does it, plastic does it, a lot of different, I don't think wood does it, but I haven't tried. That would be really bizarre. But there are a lot of different insulators that will form electrets. And usually people don't notice, because usually the voltage isn't high enough. Well, how are you going to notice anyway? We don't see electricity. We have to use instruments to detect it. So what can I say? I'm pumping current. Current is now flowing through this cell, and I remind you, both electrodes are zinc. Boy, I'm glad I put some water in it. Okay, I'm going to unplug this charger. Now, I hope that made it sound better. Okay, my power supply is off. And here, I'm shorting these together, although I need not. Those are the field plates. The field plates are now, they've done their job. I could plug them back in and make it go wild. That'd be fun. Yes, it would. So this is the residual electrical field that's stored in the guitar string bag plastic. And it is so close to that zinc electrode that it can transmit its electric field through it, because it's the permittivity of free space, which is so bad. So it's slapped up against it, and then as far as inside the zinc itself, zinc is a conductor, and there is no electric field inside a conductor, so it goes right to the other side of the electrode. Now, I think I will try to turn on the power supply. Where am I? This one's ground. Might as well be. Here. And here's high voltage coming up. And does nothing so far. Wait till I turn it on. Ready? On. Well, it's going up, but you know it's not going up that much farther. You know, it's funny. The E field was so established in the plastic that turning it on and off doesn't make much difference. That's amazing. Now, electrets do not supply current. They can't. They have no current to supply. All the current is coming from the zinc-zinc reaction, thanks to the E field. So that's terribly successful. Now, this is short circuit current. I'm going to measure open circuit voltage. In fact, there is an effect. Whether it will become useful, I would say so. Now, you can make electrets very thin. They're not, I don't know how strong they are when they're that thin, but, you know, with modern battery construction, they do it in rolls. It would necessitate a redesign because you'd have to have cathode, then electret, and then anode, cathode, electret. You know, so it's different, but what if we could add EMF? What if you could end up with a 7-volt cell? A 7-volt lithium cell? Well, these are all things that remain to be seen. Compared to my new video about a propulsion without expelling mass, it's pretty run-of-the-mill. And then I have another video where you'll see. I have this hooked up to a meter. And I hasten to point out that by turning a knob, you can make it from the high impedance voltmeter to the very low impedance current meter. So any charge that just accumulates on there capacitance-wise, it's gone like that. I made a comment on someone else's video. They were talking about the propulsion without expelling mass, and my comment just said that'll never work. I retract that comment, and the reason I retract it is because I have found something. And what I have found is a result of magnetic fields and not of the electrostatic fields that they claim for the propulsion that NASA's now testing. So what I have found is a magnetic system by which I can control position. Let's say you want to apply a torque. Well, you could turn on your thrusters outside and get your position right. Well, this can do that without expelling mass. And it does it with magnetic field. The magnetic fields are anchored to space itself. Now, this isn't only my opinion, and I was not the first to think this. That was Faraday. And a lot of people have contested the idea since, but it seems that Faraday was correct in this. At a right angle to this magnetic field is, of course, the electric field. And that's how they claim they're doing the linear propulsion. Now, magnetism is all about curve because the lines of force always reconnect. And electric fields, they're gone. They just move straight out into space. So they're orthogonal to each other. They say they used asymmetric capacitors. I would have sworn it did not work. And now I think it does. Not only do I think it does, I think this a magnetic positioner might be useful, and it is certainly possible. I have not built the device that proves this, although others have, but they didn't know what they were looking at. Now, they're not the only ones. You know, Faraday made great claims, but he didn't go quite far enough with this. I made a similar mistake. In 1994 or so, I drug about 130 pounds worth of experiments into the UCLA physics lab, and me and this professor worked them all, and you know, there was one that he said surprised him. Well, neither myself nor any of the physics professors really knew all there was to know about Faraday's work. We knew about the disk motor. But one of my experiments, I had a speaker magnet on an axle, and I had this humongous block of aluminum which I used for a conducting medium. And I would put the magnet up to the block of aluminum and spin it, and sure enough, there was no resistance from eddy currents. Now, that was a little unexpected because after all, it's made of atoms, and each atom has its moment, and they make up regions, and the regions line up together. About 150 atoms in a region, so my research has said. These regions line up, but they're discrete regions. And certainly if you had only the region and you moved it around in a circle, it would cause eddy currents in any conducting material that was nearby. But if you put them all together into a symmetrical package and you rotate it, it seems they were fungible. One line of force was as good as another, and so there was no Defy. There was no change in flux. And no change in flux, no voltage, because Defy over dt equals E voltage. Faraday claimed that axially a magnetic field does not move. It looks like his hypothesis was correct. But not only that, it can be used to defeat other natural laws. I make some pretty lofty claims in my videos, and one of mine, I claim, and rightly so, that I have engineered my way around the second law of thermodynamics, and I have made a successful Maxwell's demon. And that video is it's up there, and I hope you look at it. I'm not the only one. There's this guy, Nighthawk in Lights, and he's an experimenter on YouTube. He makes no claim of broken any natural laws, but he says and shows there that he has a piece of material which he's painted with paint, radiate, and the thing is a couple degrees cooler than ambient temperature. Now that breaks the 0th law of thermodynamics, which states that things in thermal contact go to the same temperature. So he's wisely not making any such claim. But nevertheless, it's violated.